Let's see, so just a quick little correction from last time that I posted. For those of you who are diligent enough to work this through and see it in action, this little item here is, this red item down here is new, and was just an illustration. It was one of the ones that it was the one that I left off last time in the last slide. So that's an item that dies, but it is a possibility at that point until you see the rest of the input. So just quick indication that that's a correction. All right, fine. So much for this. So announcements. I see there's lots of nice activity on the notice board. In fact, I'm really pleased to see that it appears that people are actually working on Project One now rather than the week before. Or for that matter, the day before. So this is nice. We've sort of urged you along by assigning the production of test cases to the homework. Now you probably wonder, and the purpose of assigning you to produce test cases for the homework was twofold. First, to sort of get you going on that, on at least one part of the project that people often overlook. But the other point is to emphasize that it is not necessary to have a working system or even a compiling system before you start writing test cases. This is a habit of mind that people have to get out of. Once you know what the specification of the problem is, you ought to be able to write test cases, even if you don't have anything to test them on. The sort of new area, relatively new doctrine, if that's what it is, of agile programming includes as one of its ideas that you would have you would constantly be doing unit tests, which are tests of little pieces of your program as you go along, which you can develop in advance of actually writing the pieces. And we're just doing test cases for the entire compiler, but by choosing them judiciously, you can test individual pieces of your parser. Now, you might think it's impossible for us to test your test cases. This is false. We can, in fact, test your test cases up to a point automatically. We can, for example, see how much of the grammar you cover by running all your test cases against our grammar, which we're not going to reveal to you, of course, and seeing which rules you hit and don't hit, just as an example. So there are things we can do to test things, and you should bear that in mind when thinking about whether you should shirk this particular homework assignment. I strongly suggest that you don't. Okay, other administrative questions? Yeah.
Would it be possible for you to turn up the volume?
Oh, is it? Well, I guess that's administrative. All right, is that better? Okay, good. Please, we will. I think I just discovered that there's an adjustment I have to make in the spec, I think. Please watch the board. This is just a real world, well, actually I don't have to make it. It's just a real world exercise. The customer changing the specifications just before the deadline. You know, it happens all the time. So I'll do it a little earlier than, just to get you warmed up, I'll do it a little earlier than customers usually do. Okay. Good. Other questions? Let's get started in today's topic, or today's and actually the next couple of days, I guess this is going to end up being. Yes. Yeah. Come on. Thank you. All right. Now, how are we going to prevent this from happening in the future? We aren't, evidently. Oh, dear. All right, I'll just have to not wander in that area. All right, so we've seen something called Early's algorithm, which will parse any context-free grammar, That is, it'll parse any input string against any context-free grammar, and will at least recognize the string, that is, say whether it is or is not in the language, and with a little extra work, which is described in the notes mostly, you can also extract from it, you can also figure out how to do how to work the semantic actions into it, so that you can basically take any input file that you could give to Bison, even ones that Bison or Horn reject, and it would handle them. Even weird problematic grammars, such as A goes to A, A:A, which is totally an unproductive production that would just loop forever, but the early parser will just deal with it, and it won't get upset or anything like that. So this is rather interesting and powerful, and as you might guess for anything that's interesting and powerful, it's also kind of slow in the usual case compared to what you could do. Because it keeps track of all of this, it keeps this big chart that has lots of space that grows with the size of the input, blah, blah, blah. So what the idea is to try to come up with something that's considerably faster, even if it has limitations in what grammars it can accept. Because it's really not necessary for your typical, we design the programming languages. We have control of their syntax. Therefore, we can prevent the kinds of really gratuitously complex and ambiguous grammars that might otherwise be required. And in fact, that's what people do. We generally build our routines so that, for example, we can parse them with recursive descent. What we're going to talk about now for the next couple of lectures is a technique that encompasses recursive descent, is actually more powerful in that it's able to handle more grammars without any modification of the grammar. So the general term that we use here is deterministic bottom-up parsing, meaning bottom-up means that instead of, as you do in recursive descent, what you do is you predict at each stage how you're going to produce, how you're going to match a certain non-terminal to the input. So you predict, for example, that we're going to need to use the plus production here or something like that. And the effect is that you determine the nodes of a parse tree starting from the top and working your way down. Well, the other way to do that is to work from the bottom up and stick the pieces together to form a tree as you go back up. So it's the difference between a pre-order, it's the difference between a pre-order and a post-order traversal of a derivation. And that's basically the idea. The intuition for why it might be more powerful is that you don't form a tree. You don't decide what the non-terminal is that sits on top of all of these terminal symbols down here until you have seen all the terminal symbols. So you have more information at the time you have to make a decision than you do in the case of recursive descent. The price is that these parsers are rather complicated internally, but that's okay because we have tools, and that's what they're for. All right, so we'll be talking specifically about something called LR parsing. This is deterministic, meaning that we never do any backtracking. We never try alternate routes. Now we can alter it. We can make some modifications so that we can do backtracking. But in the case of pure deterministic parsing, you don't do that. So that means ambiguous grammars. Sorry, you can't handle them, right? Because ambiguous grammars mean that you have multiple things to explore. No, can't do that. So these are purely deterministic things, so that at each point there's only one possible decision to make. We call it LR parsing. That's a historical name. L stands for left to right. You scan the input from left to right. And R means that you build a rightmost derivation. Actually, you build a rightmost derivation in reverse. Because if you think of a rightmost derivation, it keeps producing things on the right. So if you want to scan them from the left, you're sort of going to have to reverse the derivation in order to do that. All right, so let's just take an example. Here's a stupid grammar. I can call it that because actually I think George Nekula came up with this example, not me, so I'll call it a stupid grammar. All right, so here's a silly grammar. And what we're going to do is try to parse that string right there. Now, if you look at it, is that string going to work? First of all, why? I asked a question there. Why is that not LL1? That is, LL1 means the sort of thing you can parse with pure recursive descent. What's wrong with it? I think I'll just take a rest while you gradually recover from your Sunday night coma and recall the content of the course up to this point. Let's see, we saw a hand over here someplace. Yes? What? Pardon me? Yes, it's left recursive. E goes to E plus parentheses E. So that's not going to work. We're going to have to do something about it. And that's fine. So now, and this string here that you see, int plus parentheses int plus parentheses int, do you think, is that in the grammar or not? Is that recognized by the grammar or not? We see a hand there. See a hand? No, let's not always see the same hands, for heaven's sake. Yes. How do you know? Thank you very much. Yes. Could you be more specific?
Expanding the left E into, would create something of the form, if you expand the left E and then expand the E in terms of the int, and then the right E in terms of the int.
Yeah, so we can match the first int plus int to E, and then so that gives us the first E and E plus parentheses E, and then we just do that again, and we get the int. So yes, we expect this to match. We expect this to work. So let's just take a look at what happens here. Now the idea here is that we are going to invert the productions. That instead of going from E to E plus parentheses E, we're going to go backwards. When we have in our hands, in our hot little hands, an E plus parentheses E end parentheses, we'll turn that into an E if it's appropriate to do so, which in this case it will always be appropriate to do so. So we're going to start with a bunch of terminal symbols, and we're going to, and then we're going to have this. We're looking for a derivation that starts from S and ends up with this, with that sentence. So we do it backwards. We look over here to see, is there in sentence something that we can replace so as to give, in other words, does sentence have a form sort of like this, so that we can, where we can replace the beta symbol with A, and thus work our way backwards toward S. So every time we find a place where in the sentence that we have that we're working on at the moment, the sentential form that we're working on at the moment, whenever we find the right place to apply one of these productions, one of these backwards productions, we call that a handle. And the idea is that in this particular grammar, the only place where we do anything is at the handles. So the general form here is that when we're taking a backward step like this, the gamma part here will be terminal symbols that we have yet to process, or that we have already that we have yet to process, And the alpha and the beta will be things that we have processed before, because remember, we're going to be going backwards like this. So let's just take a look at how this works. So here's the grammar, here's the input string, and here's the input string again down here, so that we can see. I'm going to build a tree above it so that you can see how this works. So the first thing I do here, oops, what am I doing? Oh, I hit the wrong button. We hit the wrong thing. The first thing we do is that we recognize that int there, the red int, as a handle. Now, don't ask me exactly how I chose that int. I'm just going to say we somehow recognize that it is a handle, and we, meaning that it's one of these right-hand sides, this one or this one. And we have also determined that in this particular case, we should be paying attention to that production. Never mind how we do that. I'm just going to say, let's pretend that we do that. Well, okay, so we know that there's a production going from E to plain int. So we will take this string here, and we will reduce the handle to E. And we'll mark that we've done that by putting this new node into the parse tree that we're building, the parse tree that we're building. Okay, now the next thing to do is that we observe that parenthesis int end parenthesis, well, let's say that we recognize that that could be a handle. That int inside the int, that is, inside the parenthesis could be a handle. And we reduce that to E, giving me this situation down here. I now build this second E. Okay? Now we look at this result. We see that there are actually two possible handles we could do at this point. It looks like we could take this and turn this into an E, or we could look at this first part. But the way that we work this is that we are always going to be working as if this were a reverse rightmost derivation, which means that at this point we will be looking at the first part, the part that we've already scanned. So that is, we will see that this is a handle, the red E plus parenthesis E is a handle, and we'll turn that into an E. And we'll mark that over here in the tree by putting the E and giving me lines to all of the terminal symbols, to all the terminal and non-terminal symbols. All right. Well, now it's pretty obvious what happens next. We have that next int becomes a handle. We build this, we reduce it and build this tree over here, and then finally we do the whole thing like that, and we get E. There you are. That's the process. We proceed. If you observe the way this worked, we proceeded from processing this string from left to right. So at each point, all of the symbols to the right of the handle, the red handle, are terminal symbols. They are unprocessed terminal symbols. And everything to the left is the stuff that we have already processed. Once we process something, once we process past a certain point in the string, we don't go back and adjust something before the handle. We just keep going. Okay, so that's the idea. And now the question is, how do we carry this out? For those of you who are concerned about this, by the way, I think this came up before. Just a little note for people looking at this. The way this technology works, these animations aren't animations. They're actually separate slides. So you don't have to worry about, when you try to print this, having everything printed once or anything like that. It doesn't work like that. So, as I said, everything to the right of the handle is a terminal symbol. That's what the slide basically says. And the idea again is that we reduce a handle, a segment, a string of symbols. Reduce is the opposite of produce. Produce is where you take a non-terminal symbol and you turn it into a right-hand side, and reduce is the opposite, is what we're doing. We're going in reverse. And we don't do this until we've seen all the symbols, and we actually peek at the next symbol as well, typically, or the next couple of symbols, depending on what you're doing. So that gives us a lot more context in which to figure out what to do. All right, so let's dig a little deeper into how this is actually done, how this is actually carried out. And the way that I'm going to do this is in my examples. Is keep track of the amount of text that I have so far scanned and done something with and reduced as much as I'm going to by dividing the input into the right side, which is everything that I haven't looked at yet, everything I haven't scanned through yet, and then the left side, which has a mixture of terminals and non-terminal symbols that I have already been processing. And the dividing point is at each step is where my handle is, and my handle gradually, inexorably moves to the right until I have consumed the entire input and reduced it hopefully reduced it to the start symbol. So this gives us shift-reduce parsing, in which there are two possible operations. At any given stage, I can either say, my handle marker, my red bar in this example, is not to the left, is not to the right of a handle yet. I need some more symbols before I can do any before I have any reductions that I want to do. So I will move the handle, I will move this bar over by one, and then we call that shifting, meaning that we now consider the next terminal symbol as part of the handle. We now look for a handle that ends with the next terminal symbol. The other possibility is that we are convinced that our bar, our dividing line, is to the right of a handle, that the symbols to our left are things that we should reduce at this point. For that to be true, they at least have to match one of the productions, one of the right-hand sides. And so we will apply a reduction at that point. So that's the reduce step. So by doing a sequence of these, shifting things over, reducing when we are to the right of when we're to the right of a handle, and just keep and just doing this until we have worked our way through the entire string and reduced it to the start symbol. Always moving. These are the only two operations. So the only thing you can do when it comes to the input is move over to the right. There's no way that you can go back and say modify, do something to, for example, this E over here. Do something to that E over there, leaving these things intact. That doesn't work that way. The only place that we're concentrating on, the only place we're going to make reductions is at this, is just before this red bar here. So when we have reduced everything to the start symbol, then we're done. So usually we again, because it turns out to be convenient to define things this way, we usually throw in an end of file character at the end, and we put in an extra production that includes the end of file character. That just makes things the idea there is that you eliminate the special case of being, you essentially eliminate the special case of being at the end of the input, because the only time that you are to the right of a end of file mark is when you're done, when your entire string has been reduced, to something that looks like this. And in fact, what you can do is that if you determine that S end of file is a good thing at this point, good thing to do, then you can just say, oh well, fine. I know this is going to work at this point. I can stop right here and not go any further. So that's a possibility if you want, or you can be formal and just carry it through. Either way. So that's that's sort of the preliminaries. And let's work through this example of shifting and reducing. So here we go again. We're going to do the same thing as we did before. There's the grammar. There's the input, the part that our working memory right here. And here are the actions that we take at each point. So at this point, there are no production of the form something goes to the empty set or something goes to the empty string are applicable. And the empty string is the only thing we can work on because the potential handle is the empty string at the moment. So what we'll do is we'll shift. And when we do that, we find ourselves over here. Now that we're at this point, we will reduce by eint, which gives us that. And at this point, we will shift 3 more times before we get something useful, and that will put the input pointer right down here, and we'll move our red symbol over to there. At which point it's appropriate to reduce again, and so forth. So at each point in this process, I am making the decision about whether I'm somehow making this decision about whether to shift or whether to reduce based on something. And I'm not being very specific about what. At the moment, I'm making it on the basis of my eyes and my decades of experience and my PhD degree in computer science. But there is, in fact, a more helpful answer that I can give to the question of how do you decide which of these to do. All right, so let's just carry this through. We shift that, and at this point, we see that, we have E, and there's an end of file next, and we know that the end of file is going to be N. So at this point, we know that we've won, so we can pronounce victory at this point. Okay, now let's get into a little bit of implementation. Traditionally, what you do is you implement everything. You take the left things and you implement them as a stack. You keep them around as a stack. Why is a stack a reasonable thing to do? Well, because the way that a stack works is that you tend to access the top of the stack. It's the symbol at the top or the symbols at the top that are most readily available. That's the way the stack data structure works. And since I said that our strategy will be that we always reduce, if we're going to reduce, we reduce at the handle, which is the top of the stack, everything fits perfectly. So shifting means that we push something on the stack, reducing means that we pop a bunch of things off the stack, and then push on the non-terminal that we get as a result. And that leaves this big question of how do we shift, and how do we know when to shift, and how do we know when to reduce. And the idea here is that we're going to go back and resurrect the material in the lectures from previous weeks. We're going to figure out whether to shift or reduce using a deterministic finite automaton, which we will use to scan the contents of the stack and decide does this handle warrant shifting? Does it warrant reducing? What should we do? So that's the idea. That's the strategy that we're going to use. And the question, of course, is how do we build this thing? So the alphabet is easy enough. The alphabet will be all our terminal symbols plus all our non-terminal symbols. So we're looking at strings that happen to represent handles. Okay. So we scan everything up to the top of the stack, from the bottom of the stack to the top of the stack. And every time we see a complete handle that is appropriate to reduce at this point, and you have to be a little bit careful about that. We'll see why that isn't quite as obvious as it might seem. And then when we find such things, instead of just recognizing them the way a finite state recognizer will be, we'll take all of the final states in this recognizing machine and we'll add information to them. We'll say, each final state will say things like, oh, at this point you should reduce using such and such a reduction if the next input symbol is such and such. So that's how we're going to do this. And a parser built according to these according to this strategy is called an LR1 parser because it does shift-reduce parsing, that is, it does left-to-right scanning of the input, producing a rightmost derivation, and it looks one token ahead. It looks at the next token that it has not yet recognized to determine when it gets to a final state, when it gets to a handle, to determine whether it's at the handle and what it should be doing next, what reduction it should be taking. Okay, so it'll be labeled, in other words, it will be labeled with things like, the final states will be labeled with things like this. Take this reduction if the next symbol is such and such. The problem then is how we do this. Let's see, and I believe that's what we're going to do. Okay, so before we get in, I will leave things at this cliffhanger for a moment and take questions, and then we'll take a little break here. I haven't seen any questions. Sitting here absorbing alarming quantities of knowledge. Yes? Left factored grammar? Did that come up here? Oh, yes, I'm serious. Yes. Left factoring refers to the in an LL1 part when you're trying to do recursive descent and you have a couple of productions that both start with the same thing. The trick that you usually use is what we call you left factor them. That is to say, you replace that pair of productions with, for example, E is these symbols followed by E prime, where E prime is, and it's at E prime that you make the choice about which one to take. So let's see if we. Quick look here. So you take something like E goes to T followed by star E. Should be plus. Well, all right, never mind. Or slash E. You say, oh, look, we had the same thing in both of these, but we can factor this. We can make this be E goes to T followed by E prime, and then E prime is star E or slash E. And this trick of taking these two productions, sort of taking the common term T and factoring it out, is called left factoring. And it's what we don't have to do when we're using this particular when we're using LR parsing. It will, in effect, do it. It will do all that for us, or it doesn't need it, because it doesn't jump to conclusions about what's following this T. It waits until it gets past the T before it has to make any decisions about what to do next. Okay, let's take a break. All right, let's get back to work here. So here is such a machine. All of the, again, this is a machine, this is a finite state recognizer whose purpose is to recognize handles. In other words, I'm going to run it at any given time, I'm going to run it on one of these sentential form things here, up to the point where I get to the red line. And it will tell me whether the red line is to the immediately to the right of a handle or not when I do that. And the final states, that is the state where I am to the right of a handle, are marked, in this case, with blue notations indicating what you do when you get to such a state. And to answer a question that came up on the news group, you will see, as you can see, there are places where I have final states with transitions out of them. Yes, that is perfectly okay. There's nothing that says in the definition of finite state machines that say that the final states cannot have transitions out of them. It just says what happens when you end up there. So let's see how this thing works. So initially, my red bar is to the right, is to the left of everything. And when I scan over that, that means that the stuff to the left of it is the empty string. And when I scan over the empty string, I find myself here in state 0. And state 0 doesn't say anything, so there are no reductions to take. I have no empty strings to reduce. And it says that the next thing that it's ready to handle either an integer or an e on the stack at this point. So since there were no reductions, I know that I must take a shift, and so I do. And I see furthermore that from the machine, I see that it will be okay to shift an int, as evidenced by the fact that I will now be in this situation. And if I now scan my machine starting from the left over the int, I get to this state right here, this final state, which is marked with the production e goes to int. And it also helpfully tells me that I should do that if I see if the next character of input is either a plus or an end of file. Okay, so since the next character of input actually is a plus, I will do the reduction that it says right here, eint. I will do it on the stuff immediately to the left of the bar, giving me this situation here. So now I'll be here. Now if we run the machine over this string, starting from here at the left and running over till we get to the bar, that will take us down here to state 2. And state 2 tells us this is a final state, and we should accept the input if we see an end of file character. Well, we don't, so we're going to have to, since there are no other options here, we're going to have to shift. So we shift the plus, and that brings us, and when we do that, and when we scan over this string again, so scan over E followed by plus, we'll end up in state 3, which tells us again, well, nope, sorry, no handle yet, so you better shift again. And when we do that, we will shift an E plus parenthesis. By the way, what would have happened if the next input symbol, instead of being left parenthesis, had been plus? No? It would not recognize the string. In other words, this thing can do some error detection for us. If we ever try to shift something that shouldn't be shifted, as soon as we shift something that cannot possibly be part of a valid string, of a valid utterance, this machine will tell us that we have an error. That's a property of this. It always accepts the string that it scans when it gets to a final state is always one that could be part of a program, depending on what the rest of the string is. So we keep this process up of shifting another symbol and then running the machine over the result again, and that stops when we finally shift this other int here. So that brings us, when we have E plus parenthesis int on the stack, that is to the left of the bar, we'll go E plus parenthesis int, and we'll come down to this state which tells us that we should reduce the int to an E, assuming that we see either a right parenthesis or a plus. So, okay, we do. We see a right parenthesis. So we do the reduction. And we see I'm up here. We see a right parenthesis, so we do the reduction to that, turning that int into an E. And now we're in a state, now let's see what happens. So E plus parenthesis E takes us down here and tells us, nope, there's no reductions to take, so you better keep going. Well, okay, fine. So E plus parenthesis E, and the next thing is a right parenthesis, so we'll go E plus parenthesis E right parenthesis. That takes us to here, which tells us, oh, we're ready to do a reduction, or you can do a reduction. In fact, there's nothing else you can do since there are no exits out of this state. And so as long as you see a right end of file or a plus, you can do the reduction. And we do, so we see a plus, in fact. So we will do the reduction, which now gives us this, E plus int. So that's E, that will be E plus, that just gives us E. And then when we follow that, we see at this point we should accept if there's a end of file, there isn't. So we keep shifting. And as you see, if you follow this, we will eventually get down to the point where we have just the plain E. So at each point, we have done. So at each point, we have followed this machine through, and it's told us what to do with the input. And by essentially recognizing when we have a handle. So of course, we've now solved the problem of how you decide when to shift and when to reduce. The only problem is I haven't told you how to build this machine. That's the only remaining question. How would we get, by the way, let's just looking at this machine, tell me, how do we get down to, let's say, what is going to bring us to, what would bring us to, say, this state right here, state 9? How would you get there? Give me a program that eventually will get me to, that will eventually get me into state 9. See, one person, two people, and, okay, let's see, who has not, yes? Yeah, that's right. So if instead of expanding the thing in parentheses as int, I expanded it as e plus parenthesis int again, then that would bring me down here. So I would, in other words, if I had a program integer plus parenthesis integer plus parenthesis integer n parenthesis, then that would bring me down. That would eventually, I would get into a position where I was down here at 9. So that's what all those things down there are for. And if I keep doing that, if I go e plus parenthesis, e plus parenthesis, well, as you can see, there is a convenient little loop down here that allows me to do that as well. So we are, this machine is the real deal. It does the job. All right, at that point, but I haven't told you how to create it, and for that you're going to have to come back to the next lecture. Or read the material, of course, but I couldn't expect that.